Stars, of course, in heavier stars, the helium atoms eventually start fusing together to form all the heavy elements, carbon, oxygen, and nitrogen, so on and so forth. Since a lot of the building is with helium, which is a two-atom system, the most abundant elements are ones usually that have even atomic numbers. So like helium and then carbon and oxygen and neon and silicon, all these even atomic numbered elements. Elements like scandium, titanium, and manganese, they're not so abundant. Potassium. Okay. Yeah, continuing outward, as the temperature falls, we have a radiative zone where all the energy outward is carried by radiation. But then radiation can't do the whole job. The density is falling as you go outward. And so the sun starts to boil. And as it's boiling, it forms a convection zone. And right here, this convection, this is called the tachocline, magnetic fields get generated. And it's the magnetic fields that make the atmosphere of the sun really interesting.
George, if you don't mind,
yeah.
Is there circulation in the core in the radiative zones?
Is there what? Is there
circulation of the material, or is it?
I think there's not too much circulation in the core and in the radiative zone. I think most of it, I think in fact, helioseismology shows that the sun rotates as a solid body inside the tachocline. I may be wrong about that, but I think so. And I think the circulation starts, the convection starts, the differential rotation starts in the convection zone. So I think here it's a solid body rotation, but I could be wrong about it. Right, I must say I observed late, like all of you did, and so I'm really giving this talk in my sleep. So, you know, I've had ideas when I dream and so on and so forth, scientific ideas, and gee, when I wake up, I think, gee, what about that? And I find it's always absurd, you know, so don't, you know, I don't know what I'm saying. When the talk's over with, if any of you are still awake, please wake me up so that I can go to lunch. Anyway, you get to this convection zone, which is boiling, and then you come outward here. In the convection zone, the magnetic fields emerge in small bipoles, and they can have hundreds of Gauss flux. And these, because the magnetic field has energy, B squared over 8 pi, I think. And that's the energy density. And it's this energy and the foot point motions of this convection zone that generate the heat somehow of a corona, which is not really fully understood. Okay, if you go ahead, okay, here's the sun, and here the sunspots are cool areas. I'll show you a little more later about them. But the magnetic fields here are very strong, thousands of Gauss. And these are the regions that really generate sheared fields, or fields that are coming in at each other at angles. And coming in at angles means the fields can restructure themselves and release energy. So if you go to the next slide, okay, we have here, you can measure the magnetic field in the sun in the photosphere using the Zeeman effect, which is an effect that splits spectral lines according to the strength of the field. And the development of that and measuring these fields was done by George L. Ray Hale way back in the early part of the 20th century. And what it measures is the line of sight field, not the transverse field, although we can now measure that as well. But white and black here is simply up or down for the field. So it's either North Pole or South Pole, I don't know which. And this is an extrapolation of the field into the corona of the sun, into the outer part that you see during an eclipse. Now, because the gas is charged, I'll show you later, it will tend to follow the field lines. It doesn't like to run against the field lines. The force of the magnetic field is zero along the field lines, but it essentially keeps the particles in a helix spiraling around that way. Okay, so if you go to the next slide, you see what you all know. This is a solar eclipse. And you see how these are the magnetic field lines. Really, these structures you see out here are outlining the magnetic field of the sun. And the sun has two components to its field. It has a poloidal magnetic field out here, and it has a toroidal magnetic field because the sun rotates differentially. It rotates faster at the equator than at the poles, and so the fields get twisted and formed into a toroid. So the field is really quite complicated. Okay, but now how do we study this? Okay, so here's the next slide shows us a visible spectrum of the sun. And this is what you see when you look at the spectrum in the visible of the Fraunhofer lines. These lines are produced by the gas above the surface of the sun, which absorbs light selectively, quantum mechanically, from these various transitions. And so we can study the spectrum with a spectrometer of some sort. And in the kind we use, I found this online, there's a slit, and there's a grating, there's a mirror or an imager and a grating, and the grating disperses the light, and then the light gets dispersed on the detector, and you see spectral lines, which are really images of a slit. So by doing this and going into the ultraviolet and into the X-rays, we can see a lot of spectral lines, and we can learn a lot about the sun. So the next one, next slide. Okay, so here's where we are. We're in this visible light patch. And most of what we see that we're going to be studying, the sun's atmosphere, is down here in the ultraviolet and X-rays and gamma rays. So you can't observe that from the ground because those rays don't get to us, except when you're on a beach for a long time and you don't use sunscreen. Then you will experience some ultraviolet. So you have to go out in space to observe this stuff. So the next slide, I want to show you how we study the sun by actually referring to what we're doing here. We're observing, and here is the Ring Nebula, M57, and I'm sure it didn't look like that last night with telescopes. The lines in the Ring Nebula that produce almost all the radiation that we can see visibly are these two oxygen-3 lines down here. And so you have a nebula filter that observes these lines. Note that there's an oxygen-3, and there's something called hydrogen-1, and then there's helium-2. And when you think of the H-alpha line that we see in the daytime, that's H-alpha. So what I want to try to describe to you is why we get all these different names, what the 3s and the 2s and the 1s mean. And show you what happens when you go in the ultraviolet, what kind of spectral lines you see and where they come from. So go to the next one, which has a lot of words on it. Okay, I already told you that ions are atoms with one or more electrons removed. And the way you spectroscopically refer to them is hydrogen-1 is neutral hydrogen, hydrogen-2 is hydrogen with one electron removed, and so on and so forth. So oxygen has 8 electrons, so O1 is neutral with 8, O2 is 1 electron missing, and O3, our favorite, is 2 electrons missing, and so on and so forth. So another term that we use is isoelectronic sequence. That's a sequence of ions of the same number of electrons. So if you have a really, really hot plasma, for example, and you heat it so much that even iron with 26 electrons has lost every electron but 1, then it has this 1 electron just like hydrogen. So that's iron 26 because it has 26 electrons. So it only has 1 electron left. And that's isoelectronic to hydrogen itself. And then you have all these other ions, helium-2, carbon-6, nitrogen-7, and so on and so forth. So you're getting the idea now that all these elements in the sun that we see are going to produce a lot of different spectral lines. So go to the next one. Atoms or ions are like pianos. They emit discrete emission lines because of quantum mechanics. You can think of the electrons as orbiting the nucleus of an atom, but they're not really in orbits like the planets. They're really waves. And they all interact with each other. They're forces, so that you've got negative and positive charges. And that determines which discrete energy levels you can have. You can only have discrete levels. You can't have any old energy levels. So these are usually called, the lowest one is called the ground state. And we refer to it with value of n of 1, say, and then 2 and 3, and it goes on up. And in a real ion, these levels get split by the orbital angular momentum and so on and so forth, but we won't worry about that now. So each ion, okay, what happens when you start taking electrons away? When you take electrons away, you change all the forces. So you get a different set of spectral energy levels. So each ion has a completely different, it's like a piano tuned to completely different notes. So you can see the spectrum of the sun and UV is going to get really complicated because we have lots of ions for each element, and each ion has a different shape for its spectrum. So what happens when these levels get filled up? In hydrogen, the 1 electron sits in the ground state. In helium, the 2 electrons sit in the ground state. But when you get to heavier ions that have 3 or more electrons, they don't fit anymore in a ground state because of a quantum mechanical effect called the Pauli exclusion principle, which says that no two particles can have identical quantum numbers. And in the ground state, the electrons have the same energy and they have the same orbital angular momentum, but one has spin up and one has spin down, so they're different. But when you get to a third particle, it's got to look like one of the other two, and that's just not allowed. So these, as you add electrons to an ion to make different atoms, they fill up these upper levels. And so when you get to the top, the outermost electrons can easily be removed. It's like the sun, a star came by, could kick Pluto out of its orbit much easier than it could kick Mercury out of its orbit, because Mercury is close to the sun in a big, deep gravitational well. Okay, let's go on. Now, how do you excite and produce spectral lines? Spectral lines are transitions between the different energy levels. There's 2 ways. One is by radiation. Photons strike the atom and impart their energy and kick an electron to a higher level. And another is electrons, electron impact, which is the most common one that we have in the sun's atmosphere. And that's when an electron, a free electron that's not bound, whizzes by and gives some of its energy to a bound electron and kicks it up to an excited state. Normally, that excited state will quickly transition back to the ground state and emit a photon, and that's the spectral line that we see. And if the energy is Planck's constant times the speed of light over the wavelength, and then you can have atomic de-excitation in the same way. Well, these things just decay and produce photons. Okay. All right, so what happens as you start to heat a gas? We demonstrate this with oxygen. You start out with neutral oxygen, one over there. Has anybody got a laser? That would be helpful. No one's brought their green light? Okay. So neutral oxygen is, of course, very cold. So you find it at very low temperatures, and it's all neutral. As you heat the gas, the electrons become strong enough, or have enough energy to kick out one of the electrons of neutral oxygen. So you begin to form oxygen 2. And as you keep heating the gas, the oxygen 1 all gets ionized oxygen 2. And then as you continue to heat it, then you start to produce oxygen 3, and so on and so forth. And this is in equilibrium, where at any given temperature, you're balancing the number of ionizations by the number of recombinations. Recombination is when an electron gets captured by the ion and emits lines. So this is what the ionization equilibrium for oxygen looks like in the sun. And interestingly enough, you'll note that oxygen 3 is formed at a very high temperature, at about 400,000 degrees, something like that, or 70,000 degrees. It's very high. It's much hotter than in a planetary nebula where you see it. Planetary nebula, the temperature is 8 to 20,000 degrees. And that's because in a planetary, the ionization is produced by that hot star in the center, and that kicks the electron out. In the sun is cold compared to the planetary nebula stars. So solar ionization from radiation is negligible. So it all has to be done by electrons, so it takes a much higher temperature to produce the oxygen 3. When you get up to oxygen 7, you notice the curve becomes very broad. And it's broad because now you've gone into that lowest energy level, and that's really deeply attached to the ion. And so you really have to raise the temperature a lot before you can, this is helium-like oxygen, so it's got 2 electrons. So you've got to really raise the temperature a lot to get the next one up, hydrogen-like oxygen. And then as you keep ionizing hydrogen-like oxygen, eventually you get a stripped oxygen ion. So, and it all becomes stripped and it doesn't emit any radiation. So you can see that this is already very useful, because if you know where the spectral lines are for oxygen 3 and 4, you have an idea of the temperature right away. So you know, like oxygen 4 is formed at about 100,000 degrees. If there's equilibrium, and generally the densities are so high in the sun that we're close to equilibrium. Okay, if you go on.
How did they initially discover that one thing is 10,000 degrees and something else is 50,000 degrees?
Oh, they calculate it. They're calculating this by, they have quantum mechanically, you can calculate the cross-section for ionization and recombination. And so they go through a calculation where they just balance this, and that's how they get it. So, and that changes, of course. Okay, so I'm just showing you, I just dumped down carbon to show you what happens with carbon. The same thing. And carbon-5 is helium-like, and then carbon-6 is hydrogen-like. Okay, so going on, I thought I would illustrate this with hydrogen. We all are very familiar with hydrogen because H-alpha is hydrogen. So what is H-alpha? Hydrogen, all the energy levels in the simplest atomic case are given by this formula up here, where E is a constant, the Rydberg constant, times the atomic number squared, which is 1 for hydrogen, and then 1 over n squared and 1 over m squared. N and m are integers, and n is the energy level. So what you have here is all the transitions that terminate on the n equals 1 level. That's called the Lyman series of hydrogen. That's not what we look at with our H-alpha telescope, but that's the strongest transition. And that occurs at 1215 angstroms in the sun. All the transitions which occur on n equals 2, the second level up, are the Balmer lines. And the Balmer line is a transition, the H-alpha line that we look at of our telescope is a transition between m equals 3 and n equals 2. So this is a pretty good formula, even though it doesn't take into account spins of the electrons and any of that. You can easily calculate where all these hydrogen-like ions have spectra. So I'm just reminding you that E is h nu, where h is Planck's constant, nu is the frequency of the spectral line. The wavelength is lambda, and then the frequency is c over lambda. So for hydrogen, for example, the hydrogen 1 line is at 1215 angstroms, the Lyman alpha line. Lyman beta is at 972. Carbon 6 Lyman alpha is at 33.7 angstroms. Calcium 20 is at 3 angstroms, and iron 26 is at 1.8. We've seen all these lines. And here's your Balmer line that we look at. And here's the Balmer beta line, which you also look at for nebulae at 4862 angstroms.
George, let me just mention something which had me confused for a long time. Lyman alpha is not H-alpha.
No. Lyman alpha is not H-alpha.
Yeah,
It's what we call H-alpha is Balmer alpha. That would be a better name, Balmer alpha.
Observational astronomers did one bunch of things, and
Yes.
laboratory physicists did another bunch of things.
Yes. Oh,
And
yeah.
we end up making it
Well,
sort of
when you talk about ions to atomic people, they don't even like these numerals, 1, 2, 3. They like to put plus the number of electrons removed. So if you go on, because it's kind of fun, see what, here are some hydrogen-like spectra. Here's your Balmer series. The H-alpha line is at 65, 63 angstroms, and H-beta. And then when you get up to the 15th, 16th, 17th, and 18th, that's where they finally come. And the series limit is somewhere like around 3,650 angstroms. Now you notice that the lines, n is 2, but now m is getting bigger, 15, 16, 17, 18. Of course, you take a 1 over m squared, where m is just increasing by 1, you get a smaller and smaller differences. So the spectral lines get closer and closer together. They also get weaker and weaker and weaker because the probability of exciting them is smaller. And then they merge. There's another effect that happens. You notice I have a series limit which seems to occur, they seem to merge here, but the series limit is here. What happens is for the very high levels, because you have the gases of plasma, you have an effect called a Stark effect, which is an electric field effect that broadens spectral lines, and it broadens them more and more as you go to higher values of m. So what happens is the ions are getting closer together and broader, and eventually they merge into a pseudo-continuum emission here. And the series limit is actually over here. And it turns out by counting where they merge, you can actually measure the electron density of the gas, which in this case is around 10 to the 11. This spectrum was taken from the Skylab manned space station in '73. It was an NRL spectrometer that had film. The astronauts actually operated the spectrometer, and they contacted the scientists who were on the ground in Houston, and they had conversations, and they decided what to look at, and so that's how that spectrum was made. Here's carbon 6, which looks the same. The series limit again is you've already got a merging of the lines, and this was we took this in a laboratory using a laser plasma, and You know, how the spectral lines are identified is a long, hard story. It's a combination of theoretical calculation of where they should be, which never quite accurate, extrapolations, and then just seeing how the lines actually appear and where they are, and making guesses and finding that the guesses are self-consistent. And here we have fluorine. Both of these, this spectrum was made from a rocket spectrometer made at Goddard, but it's not of the sun. It's of the laboratory plasma, laser-produced plasma. And you see here two series limits. You see the hydrogen-like series limit, and you see the helium-like series limit. Now, there's one more effect that I've been talking about emission lines, but actually in the plasma, you also have continuum emission. And the free electrons that are out there just flying around, when they accelerate around ions, they just emit radiation. And they can emit any frequency. They're not bound quantum mechanically. So they're like violins. And so you have, in addition to the lines, you have, first of all, electrons that are falling back into the ions and being captured, producing what they call free bound emission, and that can have any energy. And then you have continuum emission, which is just this acceleration of the electrons. That's why this level here is higher than this level. You're looking at free bound emission. You can see it here and here. Okay, so that's just hydrogen, and that's where it is. Go ahead, yeah. Okay, I want to say something now about the most abundant elements in the sun. So I'm trying to tell you that we have lots of spectral lines to look at, and they come from mainly these ions over here. I haven't put down the least abundant elements. And to show you, for example, I was saying that the ones that have even atomic numbers are the most abundant, like carbon, oxygen, neon, magnesium, silicon, sulfur, argon, calcium, and iron. They all have even atomic numbers, and they're the most abundant. And just to prove to you right off the bat, here's an X-ray spectrum made of a flare. And the X-ray spectrum is made of a crystal. It's essentially, the crystal has parallel layers of ions or atoms that are closely spaced. And reflections off the different levels produce constructive interference, and you get diffraction, like a diffraction grating. And since the ion levels are very, very close, you get X-ray emission. And so here's potassium, and here's calcium. Calcium's saturated, and here's potassium. And you see potassium is an order of magnitude less abundant than calcium, maybe more than an order of magnitude, about a factor of 20. And you notice chromium and titanium, and they're all weak compared to iron. Iron is very strong. So these are what we see. We see lines from all these atoms, but the best ones to look at are the ones from the even nuclei.
Is the asterisk there meaningful to what?
Oh, that's those are Nobel gases. Okay. They have closed shells. And if I have time, if anyone's still awake or cares, the most recent thing I did involved abundances. And I found a very, very peculiar thing on the sun. I think, if worse comes to worse, I will skip that and talk about that because it's so strange. And I just published a paper on it. So the professional groups don't know that much about it either. Yeah.
How have these different amounts of elements been determined? How have you determined all of these different amounts?
They're determined in the photosphere by looking at absorption lines in the photosphere. But you cannot do it for argon or neon because they don't have any lines in the photosphere. So they are determined by combining measurements from meteorites and H2 regions and outer space. And they may be wrong, but what I found is independent of what the absolute abundance is. Anyway, notice that all the abundances too are really tiny, except for hydrogen and helium. Everything else is like nothing, you know. It's just like, so the astronomers typically refer to everything above helium as metals. No, but they're not metals, but that's what they say. Okay, go ahead. So this is just a sort of a summary of how complex this is. In the UV, between 800 and 1500 angstroms, you have all these spectral lines. This is three-bound emission forming as soon as the energies of the electrons get high enough that they can recombine and fall into a lower level, you get a recombination spectrum, you get a recombination continuum on top of the ions. And here's Lyman alpha, the strongest line in the invisible UV spectrum from hydrogen. Okay, now because lines are all over, you can get some very strange effects. There are now telescopes that I'll describe that essentially do what your O3 filter does. They image the sun in a narrow wavelength band to get a selected number of lines. But because the spectrum's so complicated, you just don't get one temperature of 2 lines. You get a whole bunch of lines. And this was made by a spacecraft called TRACE, and it had a band that was centered around 171 angstroms. It had a filter band that just showed the lines there. And the lines that you see there are mostly lines from iron 10, 11, and 12. These are million-degree lines. So this is showing million-degree lines. This is a solar flare. And these are the foot point regions of loops, plasma loops that contain flare plasma. But down here, the same telescope has a 195 angstrom filter that has one additional line that this don't have. It has a line due at 192 angstroms due to iron 24, which is a 12 to 20 million degree line. And you see a whole structure here that you can't even see up here. And these structures look almost identical because these were taken like seconds apart. You see this structure here looks exactly like that structure. And this structure here is this structure, but this is all different. And this is the flare plasma at 20 million degrees. This is making X-rays. So in observing the sun, you've got to be careful of what you're looking at and make sure you know what bands and what spectral lines are there. Okay, go on, the next one. Okay, this is just how we measured some of these things in the laboratory, how we identified them. When I started, we didn't know about lines of iron 21 or 20 or 18 or 19, where they were. It's one of the things that I did with my colleagues at NRL, and there were other people in England that also, they were our competition at the time. We identified a lot of those lines, and we did it with laser plasmas. And lasers, as you know now, there's a fusion program to make energy to fuse hydrogen into helium and make a practical energy supply with pellets. What you do is you take a pellet and you implode a big laser beam on it and compress it to densities that you need to make a fusion reaction and take something like hydrogen and make it into helium, or tritium and make it into helium. So this was just beginning, this sort of research when I started. And the laser plasma stuff, what we had was essentially a very low energy laser, put 33 to 60 joules on a small piece of metal. And you think, well, so what? How's that going to produce a million-degree plasma? Well, because it did it in 9/10 of a nanosecond. So in a nanosecond, light only goes 30 centimeters. So when you look at the power, which is energy over time, that was an enormous amount of power. And it was focused on about a 75 micron spot. And we used a lot of rocket spectrometers that were developed to look at the sun that fit in, you needed small chambers to fit in these chambers and look at these laser plasmas. So I think the next pull down will, this shows you what's happening. The laser beam comes in, it hits a target, it makes a plasma, and it can be detected by a spectrometer. And so that's what we did, and that's how we saw spectra for a lot of these lines. The next one shows the spectrum. This is the spectrum that shows iron 18, 19, 20, and 21 lines. And we focused the laser very sharply here and then took it off focus here. When you take it off focus, you spread the energy over a bigger target and you get lower temperatures. So you can see, for example, picking a line like this iron 21 line is bright near focus and not so bright here. And that helped to identify the lines. So we played this game and we finally, all the lines got identified from the lowest ionization stages, most of the lowest ionization stages, all the way up to iron 26. Okay, so it's a lot of stuff about lines and spectra, but so what? I mean, who cares? Well, what do we learn from spectral lines? Well, for one thing, you learn about the distribution of temperature, because in equilibrium, you can see, if you just see a line, you sort of have an idea of the temperature. You can also get electron densities. I'll show you an example of how that works. And the lines have a width. Although you're imaging the slit, the gas, some of the gas is moving towards you, some is moving away from you, and that broadens the spectral lines. And when you broaden the spectral line, you can measure turbulence within it. And if you shift the spectral line, you have a Doppler shift, you can measure bulk motions of a plasma. There are other techniques to measure non-thermal particles, or particles that form tails. Like the atoms in this room are governed by what's called the Maxwellian distribution. If you have non-thermal particles, it puts bumps on this tail of this distribution, and there's ways of measuring it. You can measure element abundances, and sometimes ion temperatures, and sometimes non-ionization equilibrium. So lots of things you can measure. So the next slide gives you an idea of how you would get densities. This is in the energy level of helium-like atom, and you don't need to worry about all the terminology. These are where the lines are. There are 4 lines. We'll call them W, X, Y, and Z. The lines are all produced when electrons excite these upper levels where you see they're coming from and decay down and produce photons. Now, this particular one doesn't want to decay very rapidly because it's a forbidden transition. It wants to sit there and just stay a while. Now, that's fine. Eventually it'll decay. However, if the density is high enough, another electron will come along and kick and excite the electron that's here up to this level, and it'll go down right away. So if the density is high enough, all these electrons get stolen from line Z and put into line Y. So what you get if you plot the ratio of the Z over Y is a function that looks like that, which is a function of the density. So if you go to oxygen 7 and you measure a ratio of 0.2, you know roughly that the density is like 3 times 10 to the 11. So that's just an example of how you can measure densities from these spectral lines. All these, of course, rates that you have for doing all this is all calculated quantum mechanically. And we don't know that it's all right. So sometimes we can check these things, but not always. So, okay, going on. Now, what I was telling you about Doppler effects, this is just the effect that if you have an atom moving towards you, the radiation is squished, and the line will be shifted to the blue part of the spectrum. When it's moving away from you, it's shifted to the red part. Okay, so next one shows a spectral line, just to give you an example of this, a schematic. FWHM is a full width at half maximum. That's determined by 3 things: the instrument, the thermal temperature of a line that you expect when it's just because it's a hot gas, and by non-thermal motions. And the non-thermal motions are generally there in almost all cases in the solar spectrum. In the data that I'm going to show, the instrument width is pretty fat, so we have to make the measurements very carefully. If you see a profile like this, this means that along the line of sight, you also have plasma moving towards you in this case, and it's blue shifted. So by looking at the profiles of the lines, we're getting an idea of the dynamics in the atmosphere. Okay. Let's go. So I have an experiment that I did with the British and the Japanese where we built a spectrometer, an imaging spectrometer. Basically what we have is a mirror. It's an articulated, super polished mirror. Trying to think, it's an off-axis paraboloid, and it focuses the light on the slit, it goes through and hits a grating, and then hits CCDs down here, and the radiation is dispersed on the CCDs. Now, you can't reflect normally UV radiation at normal incidence. It's just very small. However, in the 70s, they discovered a way to do this. What you do is you deposit a sequence of layers of a light and a heavy element, like silicon and molybdenum, on the surface of the glass, and that acts like a crystal with the diffraction and the constructive interference between the layers, and you can get, over a narrow wavelength band, enhanced reflectivity. How big is it? Well, like 25% peak. It's not like your aluminum-coated optics, or not 90%, but it's a heck of a lot bigger than 0.2%, which is what a coating like gold would give you. So this is a godsend for looking at imaging the sun in the UV, because you can do things at normal incidence. Otherwise, you've got to work at grazing incidence, which is a whole new cup of tea. So anyway, we built this instrument. It's actually off-axis because we have aluminum filters here to knock out the visible part of the sun. And so I'm going to show you a lot of data from that, hopefully. Okay. This is the satellite. The satellite was a Japanese satellite and we've been collaborating with them for a number of years, called Solar B. It's now called Hinode after its launch. And the spectrometer we have is the Extreme Ultraviolet Imaging Spectrometer, ICE. And up here, there's also a solar optical telescope, a big one down here, 50 centimeter diameter mirror. And then there's an X-ray grazing incidence telescope where the imaging is done at grazing incidence because that's the way it's done. And that's down here, and that goes to higher temperatures. Okay, so,
Next slide.
yeah. This is a spectrum that we got from ICE. It gives you an example of it. Now, the spectrometer, it's an imaging spectrometer. So it's imaging a slit, and it images along the length of the slit as well as along the width. And so it's like looking at something through a narrow doorway. So here we're going through an active region on the sun, an area above sunspots where the lines are very bright. And these are the spectral lines that we see. And when we take deep exposures with ICE, about 40% of the lines are new. That is, about 40% by new, I mean we don't know what they are. They're generally probably very low ionization stages of iron, like iron 6 and 7. We don't know all the lines there in 5. Anyway, this is what you get. Okay, so now that's not really good enough if you want to check theories of how things are happening in the sun. So go to the next one. We'd like to have an image. So what we do is we take the slit and we take multiple exposures across the active region. And that each spectrum is over there, and you can see it. So we got all the spectra across here. Then if you integrate over to wavelengths and stack these images one after the other, you get an image of the active region. So in this sense, we can image the active region and get a spectrum at each point along the way. And we have several kinds of slits on the Hinode spectrometer. This is a very wide slit, and what you're looking at is an active region in iron 15. It's a monochromatic image. If you click on it, it'll go. On this one over here. Yeah. So that's like a week's worth of data or something. So the imaging spectroscopy is relatively new. It's been hard to do. While imaging with filters alone and not making a spectrum is not as difficult. But for each even getting high resolution on the sun has been hard. Getting in the corona a resolution of an arc second has been difficult. An arc second is 700 kilometers or so in the sun. And you think that's pretty big. Now we're going below that, and we're starting to get images at a half an arc second or a third of an arc second. And it seems that no matter how good we get, we want more. The image gets sharper and sharper.
How close are these satellites?
This satellite is in orbit, a low Earth orbit. So, oh wait, this is in a polar orbit. It's in a polar orbit, but it's still pretty low. So it's not all that high. I had a slide somewhere that showed what it was, but I didn't put it in. So, at any rate, they're not like the LASCO satellite with the solar coronal mass ejections. It's at the first Lagrangian point. They're not that far. Okay, so going on, yeah. This shows you the multi-layer coatings. This is what the coatings on the mirror give you in terms of reflectance. There's two different coatings to get two different wave bands. So one band is around 190 angstroms, and the other is like 250 angstroms. So, and this describes something about multi-layer optics if you're interested, but you can just go ahead and Google that if you want. Okay, now that we're talking about these reflectance, go ahead. You don't need to make a spectrometer to make images. You can just put the multi-layers on and then take a picture. And that was done on the Solar Dynamics Observatory, SDO. And they get 1.5 terabytes of data a day. They have 4 telescopes, but they have 10 different bands. So each mirror must have, half of it must have a different coating on it. And they can take data very quickly, every 10 seconds. With the Ice Spectrometer, you have to take exposures that, say, are 30 seconds per each one. So it takes maybe an hour to go across an active region. So you can't get spectral imaging at a very high cadence yet, which is too bad. But when you have data like this to go with it, every 10 seconds, you get an idea of context for each spectra, what's happening at each point. So this kind of an instrument and the ice kind of an instrument are complementary to each other. Okay. And this shows you basically what a filter does. A filter will get all the lines in this waveband. And here, this filter was designed mostly to focus on the iron 12 line at 195 angstroms, which is a 1.4 million degree line. And so that's pretty good. They think mostly they're getting that, but they're not always getting it. They're also getting all this other stuff. And this band also has the iron 24 line in it, which is, well, it should be over here somewhere. Okay, go on, and I'll give you an example of. Okay, here's what happens when you take a filter image and then you take real spectroscopy images. This is an image taken by an extreme ultraviolet telescope on SOHO, another spacecraft. And it's called 284. Well, for us spectroscopists, 284 means iron 15. That's the wavelength of a line formed at 2 million degrees. So looking at that image, you say, oh, that's the sun at 2 million degrees. That's the way it looks. But now go to the next one. When you go, that's true in the active region. This red spectrum was an active region. But when you go over here, then the spectrum looks like this, and the strongest line is no longer iron 15 in green, it's silicon 7, which is several 100,000 degree line. So over here, you're not looking at a hot plasma at all. So go to the next one. So basically, there are two main lines that this bandpass responds to, iron 15 and silicon 7, and what you see depends on which is dominant. So go to the next. Let's keep going through this. So here's an ice image made of the whole sun in iron 15, a monochromatic image. There's no silicon 7 here, and you see the sun is dark everywhere in these regions. And then this is a silicon 7 image made by ice. And now if you go on, this is the image we get when we combine the images according to this passband. And you see it looks just like EIT. So the advantage of real spectroscopy is that you get the real temperature regions. But you can't get them real rapidly. So the filters give you the high time resolution and that you need to get context to see what's actually happening if you try to explain something. Okay, go ahead. So, okay, if you keep going, and we talked a lot about how you observe the sun. This is sort of what you see when you look at all the spectral lines and you put it all together, you get a mess. You have small loops that connect regions down low. They're usually low temperature loops. And then you have large loops that go out and go into the corona and reach 1 million degrees. And everything is governed by the magnetic field because all the ions tend to follow the field lines. So this is sort of what it looks like. And now you're trying to explain, well, how did this happen? What's heating it? It's basically what you want to know. And you have several candidates. You have waves, alphane waves can go through, or you can have what's called magnetic reconnection, where field lines going one way and field lines going the other way run into each other. And since I said the field had energy, that would mean they annihilate each other. And that doesn't happen. Somehow they reconnect and essentially the field gets reconfigured and you can generate heat by doing that. So go ahead. And here I was just pointing out how ions move in a magnetic field. Basically, the magnetic field is this way and the ions are moving this way. The force is actually like that. The force is not along the direction of motion. And if the ions are not moving at all, there is no force. So a magnetic field is a very weird force. It's not like the electric force. But the main thing, that the take-home thing, is that basically particles will tend to follow field lines in the form of a helix. Okay. And here's a summary of the sun in the different temperature regions, 5,800 degrees. And here you see around the sunspots, these are called granules, these things up here. And the granules are like 1,500 kilometers across. And they're on constant motion, and they provide the foot point motions that heat the gas because they move the magnetic field around. And then as you go to higher temperatures at 100,000 degrees, you see lots of little structures. Those are the little loops I showed in the first slide. And then as you get to higher temperatures and millions of degrees, you get a much more amorphous looking thing because the structures get much bigger. They look nice, more smooth. And finally, you get out into the solar wind, this is an image from a coronagraph. And what you have here, this circle is the sun, and this is an occulting disk to block out the bright light of the sun, and this is the atmosphere streaming outward at 2 million degrees. Okay. So here are full sun images in the Ice Spectrometer to show you what the sun looks like starting at a very low temperature, helium-2, and 100,000 degrees, and going all the way up to iron-16. And you see at 2.5 million degrees, the sun isn't very bright, pretty dark. You see it sort of in the corona peaks around 1.6, 1.4 million degrees. And you see the tiny structures at the low temperatures and the more amorphous structures at the higher temperatures. Okay. So you can see this even above the limb. The slit of the Skylab spectrograph was laid tangent to the sun, and we looked at spectral lines from all these different ions, carbon 1, sulfur 1, oxygen 1, and you see the low temperature ones fall off very quickly, and the higher temperature ones peak according to their temperature of formation. And when you go into the coronal holes at the poles of the sun, you have field lines that are mostly open, so that they look dark in the coronal images, and it's because they can't trap the gas. The temperature in the coronal hole never gets much above 1 million degrees. And these field lines, the lower temperature lines around 220,000 degrees get stretched. And you can see, this has all been plotted. So by using spectroscopy, we've really defined pretty much everything you see in the sun. We determined the physical properties of the atmosphere, the temperature and the densities and the motions. Okay. What we would like to do is connect everything. We would like an instrument or a satellite experiment that could image everything at the same spatial resolution all the way from the photosphere to the corona. We haven't done that. The Hinode spacecraft has a solar optical telescope that can image 1/10 of an arc second or so, 1 or 2/10 of an arc second. But the ICE and the X-ray telescope, we can only do an arc second, a pixel. So we're way off. And we can't trace the structures we see in the corona to the surface because you get to the surface and there are many, many possibilities. We can't connect them. So we'd like to trace them. So you can click through that pretty fast. That just shows what happens as we go to higher temperatures. Going from calcium-2, low temperature, to H-alpha, and click again. And we get, now we go up to helium-304, and already the resolution is getting worse, 1.2, and then we go to 171, 1 million degrees, if you click again, and you see things get even fuzzier. What we want is a space mission that will connect them all. We developed such a mission called Solar C. Unfortunately, it cost $1 billion. So we wanted 3 space agencies to work on this. JAXA, the Japanese one, NASA, and the European Space Agency. And nobody has the money now. They're just out of money. Everything's going into solar probe at NASA. And so the thing is sort of sitting there in limbo. But it must be one of the hardest worked on projects anyone ever did. We spent years on it, and we have fully developed payload to make it essentially a payload that will do all this and get spectroscopy all the way through from the photosphere into the corona. Okay, go ahead. So I was showing you the sun basically here as a picture. That's the way we used to look at it. But the sun's actually very dynamic, so keep going and keep clicking. We'll never get to lunch. You can click on all these panels. They're all movies. And you see that's a granular motion that you see down there occurring all the time. And then this is the motion at 1 million degrees. And this is the outer motion. This is a coronagraph that looks sideways outside, and you can see the solar wind streaming out. You can see the stars in the background. And here you see a coronagraph picture taken from SOHO, and you can just see there's a 2-week period, and you can see the stuff streaming outward. And up here in this one, if you put this one on, you see those structures around, essentially around the poles called coronal holes where the fuel lines are open, and everything is very, very cold. So the sun is in constant motion, and this motion, when you start to look at theories with this motion, you can understand a lot more than if you just regard the sun as a picture. Okay. Go ahead. Just keep click again. Okay, so here's another example. This was taken with the helium filter on SDO, and you can see a solar flare occurring, and you just see all this plasma moving out, and it doesn't form symmetric patterns, and that's terrible for theory, because it's easy to develop theories when everything's symmetrical. When things aren't symmetrical, and they're asymmetrical, and it's a jumbled mess, and they're overexposed like that, it's very hard to do that. But anyway, this is what you see normally. Go ahead, if you click away. This is taken recently from a satellite called IRIS. These are the silicon-4 lines at 1,400 angstroms, formed at about 70,000 degrees. And this shows you the tiny little loops that I showed on the schematic, and how they're in motion. They're not just sitting there. They're in constant motion. As energy gets dissipated in the atmosphere, it forms little heating pockets, which then cool off, and then other heating pockets form in other places. Now, what causes the heating? Well, waves could cause a heating, alphane waves that propagate into the atmosphere and damp, that essentially dissipate their energy locally. Another thing is nanoflares, where nanoflares are tiny little things where you have the gas is heated to maybe 10 million degrees and then cools sporadically and spontaneously. And this is produced by reconnection, where the field lines go opposite each other. So, okay, so go ahead. So here's the corona, and it shows you emotions in the corona, again from the SDO spectrometer. So basically what we're trying to do is understand all of this. When we get a spectrum, we know that if we had multiple spectra of that region, that we would see all sorts of motions. So to try to tie things together with the theory, we have to combine this ice data with data like this, with the filter data. Okay. So the solar optical telescope shows what you see on the surface of the sun. You see these little things called spicules, which are jets that fly upward. Some of them fly upward very fast, much higher than most spicules, and some people think that this actually dumps mass and energy from the chromosphere into the corona and heats the corona. You can see this with your H-alpha telescope. If you have a Solar Max 2 or a Lund telescope, and you're looking at the whole sun, if you look at the limb of the sun very carefully, you'll notice two components. There's a very sharp inner boundary, and that's the part of the H-alpha filter that's in the continuum. Because on the disk, your H-alpha line, which is Balmer alpha, is actually giving you a Fraunhofer absorption profile. When you go above the limb, it becomes an emission line, and you just see H-alpha emission. And you can see that in your telescope. I thought the optics was bad, but then I went to higher power, about 80 power. I used a PowerMate and a 25 millimeter CMEX eyepiece that they give you. And you can see this H-alpha thing, and you can see the little, it's ratty, it has a ratty edge, and that's the spicules. So that's the chromosphere, and it's about 2,500 kilometers thick. Go ahead. And here's these, in all of its glory, taken of the solar optical telescope. This is a high-resolution telescope, a 2/10 of an arc-second resolution. And this is the prominence where the gas is essentially held above the sun by magnetic fields, and we're trying to explain why. And you can see it's difficult to do that. MHD programs are developed, magnetohydrodynamic programs, to try to explain this. But it's really difficult to do because nothing's symmetric. Everything is wild. Okay. Now, because the sun has this magnetic field, that, as you all know, the sun is a dynamo. There's a sunspot maximum, sunspot minimum. Every 11 years, we have a sunspot maximum. Every 22 years, the field changes polarity, north to south. When I was in high school, was here, 1958. This is the biggest solar maximum ever on record. And I remember looking at the sun with a 4-inch telescope. I had my observing notes as an amateur, and I counted one day 16 spot groups. How many do you see out there today? You're lucky to see a single sunspot sometimes today. So over my career, I've the biggest possible maxima you can imagine. And in a sense, if I'd been born here, down here, I might never have been a solar physicist because the sun would have been too boring. But as it was, we developed all this space stuff right at the peak of the sunspot cycle. So, of course, now people here are somewhat suicidal because the sun seems to be petering away. So, okay, next one. So here's what, if you take a picture in X-rays, this is a solar X-ray telescope on Yoko, and this is a solar maximum, and you go to solar minimum, you see what's happened. The sun just gets very, very boring. That doesn't mean it won't produce flares or things that could disrupt our space weather thing, but nevertheless, it's not nearly as interesting. Okay, so active regions are where the sunspots are. And they're sort of like where the bad guys are, the thing that's producing the space weather effects. So here's your sunspot and all this granular motion. And you see the sunspots emerge. They just come out of the surface, and we actually have a program now to try to detect this before it happens using helioseismology. But I don't have time to talk about that. The fields are very strong there, and they mix together and they form a jumbled mess, and that makes it possible to get solar flares and coronal mass ejections. So going ahead, here it's from Ice, and that's a movie, if you play it, where we've mapped the whole active region's temperature structure. We go from very low degrees of ionization to higher, magnesium 6, and then we go to iron 8, and so on and so forth, and that's hotter and hotter and hotter gas. So you see what the active region, where all the hot gas is. And we never could do that before this. So this is really useful when you're trying to understand how this thing works, when you have theories like nanoflare theories to explain all of this. So here at iron 13, we're at about coronal temperatures of 1.4 million. And then we go to 14 and 15 and 16, we're going to higher temperatures. And the higher temperature regions are all over here in a jumbled mess of very close loops. You can't even resolve them because they're all so stuffed close together. And you notice how smooth and amorphous it now looks. The structures are much bigger. Okay, so we've tried to see if this nanoflare idea would work. So the next slide. This is a complex thing, but basically it's simple. The emission measure is a quantity that you get when you analyze the spectral lines. It's a square of the density times the volume. It's physically meaningless quantity. But the nanoflare theories can compute it. They can compute what it should be. So now in a nanoflare model, you have a loop filled with hot gas, and you have these little flares going off that heat the gas to 10 million degrees, somewhat randomly in the loop, and then it cools. And it cools so rapidly that the gas can't drain or anything. So the emission measure, the square of the density times the volume, should be flat, that is in temperature, because you have 10 million degrees everywhere, and you have 100,000 degrees everywhere, because anything that's hot becomes cold. So we don't see that. This red curve is the distribution of this quantity with temperature, and you see it tend to peak at values like this. So all the nanoflare people are somewhat upset by this, but that's too bad. When theorists get upset and professionally, what they do is they start adding bells and whistles. So, and then they can add, the theory goes like this. You go into a theorist and you say, I've computed A against B, and A should increase with B. And the theorist says, oh, it's great, it's just what I predict. And then you look later and you realize you did it wrong, and A actually decreases, or B actually decreases with A, and you go in and say, I'm sorry, it's the inverse. And say, that's even better. So this is the way this goes. So we're now having battles with people about nanoflare models because we're computing this emission measure distribution for a variety of different elements all together, and these things reflect the spectral lines, never mind, but they're all the lines I've been talking about. And you actually know more about this than you think. This is just the inverse of the curves I was showing for the ionization equilibrium. And we're not coming to grips with this. We're not getting agreement. Okay. Now, one thing we found that was really interesting with ice, I mentioned dynamics. Here is an image of an active region in iron 12. So that shows you, 1.4 million degrees, what the active region looked like. We can make a Doppler map, because we have spectra for all of this. So when we plot the wavelengths of the lines, we find where white means you're at the rest wavelength, no motion. But at the edges of the active regions, and here, we always find these big outflows. When we see blue, that's something coming towards you. Red is something going away from you. And this stuff is moving at about 45,000 to 336,000 miles an hour. And this was a new discovery in a sense. It was predicted by some people. So I wrote a paper on this. Unfortunately, the people who predicted it refereed it. And then the papers get very quickly accepted. It's provided, of course, if you don't have one of our references, I'll say you should also reference this paper. So we added all that, and it could be that this plasma that flows outward here becomes part of a solar wind. It could make up a good deal of a solar wind. We still don't know for sure, and that's one of the things we're working on. So go ahead.
George, on that picture, doesn't there sort of need to be as much red as blue to balance the net, or this is just stuff coming in?
Well, it's pretty much in here, it is true. This stuff goes out and gets replenished, but you're right, there has to be stuff going down. But this is denser, so there could be a lot in here that that you don't see here. But it's a good question. Where is all the red? Whereas there should be as much going up as down. Actually, in the transition region, that is in the region around 200,000 degrees, it's mostly red. It's mostly going down. So maybe a lot of it goes down when it's colder. So this is hot. So maybe this hot stuff goes out, the colder stuff goes down. Okay, I said I wasn't going to say much on coronal mass ejections because we discussed this and decided this wouldn't be a space weather talk. But coronal mass ejections are seen best in filtered images, and either filtered images or white light images. You see these things in the white light by just scattering of the photospheric radiation off the 3 electrons in the gas. And there's all sorts of models of mass ejections, but basically a flare or a mass ejection involves a structure like this with a pinch-off effect. And what happens in here is that the plasma pinches off and forms big structures that move out very rapidly and it sends energy to the chromosphere and bubbles gas up from the chromosphere to form a flare. So these things have all sorts of different shapes. If you go to the next one, they put all this together and they think by reconstruction of these three-dimensional things that the basic coronal mass ejection is a giant magnetic helical flux tube that moves outward. And that's what you actually see, and that's what comes to the Earth. And sometimes these flux tubes are filled with solar energetic particles, very high energy particles that really screw up the spacecraft. They can come into the polar regions and screw up your power grids and cause a solar weather storm of the century and wipe out civilization as we know it. So anyway, that's a sort of a structure we think exists there. But I'm more interested in the flares. So go on, some more. Okay, here above we have an X-ray detector flown on the geosynchronous environmental satellites, producing X-ray emission around 8 angstroms and 4 angstroms. And you see every time there's a peak, there's a flare. And this is an SDO image taken in a filter around 131 angstroms. SDO, unfortunately, saturates most of the data for flares. And they don't really care. They say it's not a flare emission. But at any rate, those big bright blobs you see are a lot of saturated data, and the flares are self-occurring. Okay, well, flares are of particular interest to me. Go ahead. Because here's the cartoon for the flare. Magnetic reconnection is where the field lines come in, and one's going up and one's going down. And what you have is a field that looks like this, and then plasma comes in his point, and these field lines get squished together and they reconnect to form these loops. They form a loop that looks like this and a loop that looks like that, and they send jets of gas out and jets of gas and energy down. And energy that goes down the loop goes all the way into the chromosphere, the cold part, and heats the gas here to millions of degrees, and it bubbles up into the loop and produces this X-ray pulses that you could see in the last thing I showed. In other words, you need a dense loop to make a lot of X-ray emission. So this is called chromospheric evaporation if it occurs at the foot point. And we've always wanted to observe it in different temperature regions because we have models for it and see if the models fit the data. So in the data that we had from the X-ray instruments, we couldn't image. We could get the spectra and we saw the stuff coming up, but we didn't know where it was coming from. So the next image, that's just another example of this to show you how complex the flares are. These are the loops, and you can see it looks like a big slinky. And you get propagation all along the loops. But supposedly any loop has foot points, and the foot points are, let's see, where are they going to be? Down here and over here, and bubbles hot gas up into the loops. Okay, good. If you go to the next one. So here's data from the Ice Spectrometer, and we had a hard X-ray burst. There's a hard X-ray satellite that images data in around 25 to 50 kilovolts. And these are spectral, just a slit spectra from ice. And this is the image going up this way, but it's just the slit spectrum down this way. So what you see is the Doppler shifts along here. And you see Doppler shifted stuff here, and you see Doppler shifted stuff here. And here are the images from the hard X-rays. So the hard X-rays indicate particles that were made in the reconnection region and went into the chromosphere. So they bubble the stuff up. So, okay, what do the spectra look like here and here? So the next image, I hope shows that, yes. Okay, so the image, the histogram image comes from this region. And it shows the spectral line of iron 24, the 12 million degree line, at roughly the rest wavelength. And then it shows you, though, that there's a component that's blue shifted. So this region is evidently, along the line of sight, a composite of a loop top and a foot point. And the foot point should have purely Doppler shifted emission. As the energy hits the chromosphere, and boom, explodes. And so down here, that's what you see. Down here, everything is Doppler shifted, 280 kilometers per second. And this is consistent with what the theories predict for this sort of thing, with the X-ray emission that we see. So we're making some progress in understanding this. So to the next slide. Now you want to know what happens at different temperatures in this foot point region. So the histogram is the iron 24 that you saw Doppler shifted by 280 kilometers a second. And these are the profiles you get for the colder lines, iron 14, iron 15, and iron 12. And they're shifted a little bit, but some are actually moving down. Some are actually Doppler shifted to the red. And that's what we expect, because when you blow off part of a chromosphere, it's a rocket effect. So this stuff that blows off kicks the conservation of momentum, pushes down on the plasma that's left behind, and that's basically colder plasma. So these profiles are basically agreeing with what the models say. So that was a nice result that we're going. Now I have a bunch of stuff on X-rays, but how are we doing on time here?
Got about, let's see, 45 minutes.
45 minutes, okay.
Leave time for questions.
Yeah, including questions.
Yeah, okay. So tell me when you're exhausted, because I'm
Maybe a little bit about X-rays.
yeah, X-rays here. All right. When you get the X-rays, most of the lines you see are from hydrogen and helium-like ions. And these, remember the graph I showed of the ionization equilibrium? The helium-like ion in particular is formed at a very large temperature. These are all sulfur 15, calcium 19, iron 25. These are all helium-like. So you really, by seeing the line, you don't really know the temperature because it could occur over a very broad range. Here's iron 26, Lyman alpha hydrogen. This is the hottest line that we see with any strength. And that's like, it goes up to 100 million degrees. So this is a merger of seeing thermal plasma mixed with the non-thermal plasma created in flares by reconnection and particle acceleration. So, okay, the next slide shows the kind of spectra we get there. These are taken of crystals, and with crystals you can't image very well. So basically we're looking at an entire flare. We don't know where the lines are coming from, but this is what you see between 1.85 and about 1.9 angstroms. And all these lines are very highly ionized lines of iron, with the helium-like line over here, and then iron 24, and iron 23, and iron 22. And over here, the calcium spectrum, same thing, helium-like calcium, and then there's these lower ionization stages. Now, it turns out we're very lucky because the lower ionization stage lines aren't formed quite the same way as these lines. The resonance lines, that is the strong helium-like lines, are formed by electron impact, like I showed early in the talk, where electrons just come along and excite an electron up to the excited state and it falls down. There's another atomic process that gets important in the X-rays called dielectronic recombination. And in that process, a helium-like ion, which has 2 electrons in the ground state, a 3 electron comes along and falls down into an excited state, but it also kicks one of those helium-like ions, electrons, up into an excited state. So now 2 electrons are in excited state. And this is called a satellite line. And the probability for doing this has a different temperature dependence than the formation of the helium-like line. The helium-like line and the dielectronic line are formed from the same ion, the helium-like line, the helium-like ion, but the excitation process is different. So because of that, by measuring the strengths of these other lines, like, where's the line J? This line J, the ratio of J over W is a very strong temperature indicator for flares. And over here, K over W is very, so we can measure the temperatures of flares. So go ahead. And you get the same thing with the hydrogen-like line. This is the hydrogen-like line. There's actually 2 lines because now the interaction between the spins and the angular orbital momentum splits the levels. You can actually see it in hydrogen-like ion. You can measure the temperature of flares with the hydrogen-like line as well. So going on is a result. And so what we've done here you can see it. Here's 3 flare spectra of a cooling flare where I've normalized all the data to this resonance line of the helium-like line. As the flare cools, these lower ionization state lines pop up and become very strong. And by taking the line ratios, we've got the temperature. So here's the temperature as a function of X-ray spectral class. And X-rays are classified by the GOES data into different classes. Each class differs by an order of magnitude of X-ray intensity. And they go, you have A, B, C, M, and X flares. Why you don't have A, B, C, D, I don't know. Somebody asked that question. And I think somebody in the Air Force years and years ago decided it would be A, B, C, M, and X. But X flares are the big ones. Last year, at Almost Heaven Star Party, we saw an M flare out here. It was really exciting. It was really nice. And we measured mostly M flares of Yoko, and these are the temperatures. And as you see, as you go to higher class or more intensity of X-rays, you get higher temperatures. And if you extend this plot, this is the plot of the emission measure, the square of the density times the volume. And if you plot this against this, extrapolate this, you get temperatures that have been gotten in stars. And these are stars that have much stronger magnetic fields or much more convection than the sun does. So, okay, good. Oh, I'm finally getting to this abundance thing. So if you're up for this, okay, go ahead. The abundances in the sun are not constant everywhere. We have what we call photospheric abundances. That's usually what astronomers use and put in their tables, because that's the only abundances that we seem to have. And that's the measurement of abundances in the photosphere. That's the cold part. Now it was found by looking at energetic particles at the Earth and by looking at the coronal spectral lines that some lines get enhanced in the corona. And the lines that get enhanced in the corona are, peculiarly enough, lines that have very low first ionization potentials. And you say, well, that's crazy, because by the time you're in the corona, you've ionized way away from the lowest ionization potential. And what happens is that in the photosphere or chromosphere, the lines that are easier to ionize, the atoms, get ionized first. And the neutrals, like argon and neon, stay neutral. And then you get an effect. You can get an effect called a ponderomotive force, which is a force that can pull the ions up into the corona faster than the neutrals. So you can get an enhancement of ions of low first ionization potential in the corona by a factor of 3 or 4 is what it is. So the coronal abundances are different than photospheric. And it's real important in theories because frequently a theorist wants to know the rate at which a plasma radiates, and that depends on the abundances of the ions. So there's a detailed explanation for this. There's a model for this that very few people understand, but anyway, Martin Lamming is at NRL, has got what's called a Solar Physics Living Review. That's a thing that can get updated and updated as you go. It's been published. So the standard interpretation is that the low FIP element abundances are enhanced in the corona, high being FIP as first ionization potential, high FIP coronal abundances are the same as in the photosphere. Now, in some stars, you find an inverse situation. And Lamming's model is nice because it accounts for both cases. He can explain both. So, okay, the rock stars of high FIP elements are helium, as very high FIP, neon, and argon. So these are elements that are the same in the corona, supposedly, as in the photosphere for their abundances. The low FIP elements are potassium is the lowest, 4.3 eV, sodium 5.1, aluminum and calcium 6.1. We also know that the abundances gradually can go from photospheric to coronal. So go ahead to the next one. But this is just a summary of what I just said. The boundary, roughly, where you go from high to low FIP is at about 10 electron volts. So these abundances of the high FIP elements are the same as they are in the photosphere as they are in solar energetic particles of a corona, while these low FIP elements are elevated by a factor of 3 to 4. Okay. I think I may be too tired to explain this, but this is taken on Skylab, but it shows it very nicely. This is a magnetogram that north and south magnetic poles, taken on 2 days, August 30, August 31. You notice that over here is nothing, and on August 31, a day later, there's an emerging flux region. So there's some flux that just comes out. There's loops, magnetic loops that have just come out. Over here, it's hard to see, but these two regions look the same. Now over here in our data, we have lines of neon 6 and magnesium 6. And magnesium is low FIP, very low, and neon's very high. So in this region where the flux is the same, it hasn't changed much. Note that all these lines marked magnesium are brighter than the neon ones. So this is a region where the abundances have become coronal from the photosphere. Here's a newly emerging region. When it's newly emerged, it's still photospheric. So in this region, the spectrum shows that the neon lines are the strongest lines and the magnesium lines are weaker. So you can see the effect. Now these two lines, magnesium 6 and neon 6, are formed roughly over the same temperature interval in ionization balance, like those curves I showed you. So there's no temperature effect, there's no density effect. The only effect that could really do this is abundances. Okay. All right, so what did I find lately that's interesting? Well, with ice, we've been trying to measure the abundance of argon to calcium in flares to see if it's coronal or photospheric. My buddy that I work with believes that in flares, the gas must be all photospheric because it's blown up right out of the photosphere. How would you have time for any fancy ponder motive force thing to do anything? I mean, you're blowing stuff up, you heat it up to 20 million degrees and it just explodes. So it has to be photospheric. So what we did is we made images of flares with ice data, and I cut out a little box just to show the flare because the ice spectrum is a much bigger area. And I wrote a computer program that I could click anywhere in the flare and I could see what the abundance was. I calculated the ratio and I could display it. So that way, here's a loop-like thing and here's a loop top and here are foot points. So I could look at the foot points and see at the foot points we definitely expected photospheric abundances, but maybe at the loop top for some reason we wouldn't get that. And this just shows you that these calcium and I had an argon line don't change much with temperature, but you can forget that. Go on. And here's what we found, and I called this Alice in Wonderland. We found mostly coronal abundances, much to my partner's dismay. He wanted to see photospheric, but we didn't. We got coronal abundances. There's a third offer in a paper, and he was happy. He liked that. This curve is what we usually see. This is an argon line, argon 14, and this is a calcium 14 line. And you can see that calcium is normally much stronger than the argon. But I found clicking in some places, I got this. I got this crazy thing, a histogram, where the argon was now much stronger than the calcium by a huge amount. So when the two lines would be equal, if the argon line would equal the calcium, that would be photospheric. But this thing is 7 times stronger than that. So this is basically an inverse Fipp effect in the sun in a very tiny region, in this spot region right here. I didn't find this often, but I found it, and it's real because I found it in several places. So I plotted out the spectrum, and I took it into Harry, my friend, and I said, Harry, look. And he looked at that, and he said, you know, George, that you have a remarkable ability to fabricate the data. And of course, he didn't really mean it, but it's not fabricated. I didn't do it. There's no theory here. There's no, you know, like saying, well, I'll make this assumption and that assumption, and you might not agree with. This is just the data, and it just looks like that. And now he said, oh, but wait. You could have an unidentified blended line here. There are many unidentified lines, and it's kicking it up, because this is also near a sunspot. It might be cold. Well, it turned out that by accident, we had another argon line as well in the same database. And when you looked at that, this is the normal situation where iron 10 would dominate the spectrum instead of this line. This should be argon, this should be iron 11. But here, in the case where you see this, you see the argon 14 line just blows everything away. So this argon 14 line and this argon 14 line track each other. So I call this Alice in Wonderland because I think in the story Alice goes up and down in size. And so this is what's happened here. So if you go on, I made a composite image of this by combining from SDO the 193 iron 12 filter, the 1700 angstrom filter, and a magnetogram all together. And at this point, it goes into the sunspot. So going on, I had some details of this. My boss was very excited about it, so she reported it to the heliophysics division panel for NASA. And basically, this is the largest abundance anomaly of its kind in the known observable universe, as far as I know. There's nobody has seen an effect like this. And it's only over very small areas. Now we can measure, it turns out that the two argon lines are density sensitive. So we can measure the densities, and the densities we get are like 4 times 10 to the 10 up to 10 to the 12. They're reasonable for flares. So everything is reasonable. Go to the next slide. For those of you who are now confirmed spectroscopists who just love this stuff, these are where the lines occur. And we have some additional argon lines that we didn't get in this pass in this kind of program that we had. And we're going to look at all the argon lines. So now there's a third author on the paper here, and the third author is retired. And he's an older guy, and actually he was a guy interested in this too. So I needed to get his address for a paper, and because they want the addresses of all the authors. So I sent him this monster Fipp effect discovered attachment. I said, well, I'm writing a paper, I need your address. So I expected him to be very excited about it. So he sent me back an email with just the address. And I thought, well, okay. So I phoned him. I said, hey, Yuri, what's going on? I said, did you see what was found? He says, yes, George, I saw it. He says, I don't believe it, but that's okay. So he didn't believe it either at first. So it became sort of a hard thing to understand. Anyway, if you go ahead, this is the density sensitivity of the two argon lines. And what we see, all the data we had goes between 1 and 2. So the densities are somewhere in this range. We have like only 4 or 5 examples of it. 3 of the examples are shown in the next one. So Harry, who I work with, essentially made images of all these, and he plotted he has an image of the argon over calcium ratio, And then he has the argon image and the calcium ratio, and he has two images from AIA. And he also noticed that it appears in helium as well. And you would expect that because helium is the highest FIP element. So it appears to be an effect only of the high FIP element, the very highest FIP elements. And here, these are the same kind of spectra that I just showed you. So we don't know where it's going to go. What we're going to do now is first make some programs to get all the argon lines. And then we're going to try to take the data we have and look at the SDO data in time and see if we can figure out what could be going on. Okay, so that ends that. And then I just want to go ahead.
And George, I think we need to wrap up.
Yeah, we're going to wrap up right now. So the solar wind goes out. The solar wind goes out to the edge of the solar system, and that's the planets. And go ahead. And the big questions of astrophysics are what heats the corona, how does the sun's magnetic field. We have all these ideas, but we cannot show for sure that any one of them works. It's like saying, you know, my arm hurts. Why does it hurt? You say, well, there are many reasons. Maybe you sprained it, maybe this or that, but we have no way of knowing for sure. Go ahead. Okay, these are the mechanics. This is just a review of what I've been saying, how you might, the main theories for heating the atmosphere. So, going on, and here's how you can stay informed. You can download some of these data daily, so you don't have to hear a talk about it. And you can join NOVAC, which is a great way to stay informed about astronomy, period. Go ahead. And that's it. Okay, thank you.